Okay, internet voting. These two words generate a lot of controversy. For instance, there are people that are in favor of using internet voting since they think that it can improve the democratic process. For instance, can help to set up a democratic process that for like e-participation that can enhance the decision making of governments. But on the other hand, you can find people that are completely against internet voting. Why? Since they think that the security of internet is not enough to guarantee the integrity of elections. So internet could be a way for instance, for rigging elections or manipulate the final results of an election. And why? Mainly, one of the reasons is that it's considered that internet is not providing enough transparency to the voter. And transparency is of paramount importance in any kind of election. It doesn't matter if it's electronic, it doesn't matter if it's based on a traditional means. Transparency is very important to guarantee that the election is behaving properly. If we analyze how transparency works in a traditional election, we can see that it's mostly based on using tangible physical elements that can be supervised by human means. So for instance, voters are using a paper ballot for registering the voter intent, and the same voters are putting this paper ballot in a paper envelope. This envelope is put in a ballot box that is also physical, usually transparent, and an electoral board is checking that only the eligible voters are allowed to cast a vote, and they are only casting a vote. Also, observers are supervising everything in a polling station and can check that, for instance, at the end of the counting process, nobody is, or the electoral board is not manipulating the votes that has been cast by voters. But what happens when we move to an internet environment? Everything is happening in a logical environment. That means that the only physical part are computers. Therefore, how can the same voter verify that the voter intent has been properly registered by the computer and is properly stored in an electronic ballot box? And the same happens with the election officials. How can we ensure that the computer that they are using is really providing the results of all the votes that has been cast through internet? So how can, for instance, provide this transparency of e-voting? If we start thinking about standard cryptography can provide some protection of the information of the data that is registered by the voter. We can encrypt the voter intent and also we can digitally sign this voter intent to prevent that nobody is manipulating this vote. However, the only thing that we can verify here is that the vote belongs to a valid voter, since we can check the digital signature of the vote. But can the voter verify that the encrypted vote really contains her voter intent? Or in the other side, when the votes are counted, you have votes, you decrypt the votes, and you provide results, but are the results really related to the contents of the encrypted vote? So standard cryptography provides data protection, but for sure to provide verifiability on e-voting. Therefore, we need to move to more or less what is known the next generation of cryptography is, and we need to use advanced cryptography. Why? Since advanced cryptography mainly is providing proof of the proper behavior of the cryptographic algorithms. And then this will provide verifiability to the cryptographic processes. For instance, one thing that we can do with advanced cryptographic processes is that we can operate cryptographic data. And operating this data, we can, for instance, generate the operation of the contents of this cryptographic data, but still encrypted. So we can operate information without decrypting them. We can preserve the privacy of the information. But the most powerful tool of advanced cryptography are something that is known as zero-knowledge proof. I know that sounds very strange, but mainly the idea is if we use as reference two proofs that are the most common in cryptography, and especially in cryptographic protocols for e-voting, if we think about, we can use proof to verify the correct decryption of the process, or proof that can be used for verify that if you have two different votes with different encryptions, they still have the same contents. So nobody is manipulating the votes. The proof of correct decryption, mainly, what they are doing is they are providing, or it's a way that the entity that is making the decryption process can generate a proof to any verifier that can use to check that if I have this content that is decrypted from the vote and I have this encrypted vote, using this proof, I can check that the content decrypted is really the content that was previously encrypted, okay? And the most important part is that the verifier can do this without having access to the private key. So we can still preserve the privacy of the election. In the case of the plaintext equivalence, it's similar, but it's just to check that we have two votes encrypted, but they still have the same content. So once I did this, let's do an example about how is currently used these advanced cryptographic practices or algorithms in a real election. This is, for instance, used currently in Norway. And this is a voting card that is used by the voters to verify that at the end, the encrypted vote really contains the selections made by the voter. And what we have is, in one part, voters receive what are the candidates that they can cast votes for. And they also receive another part that contains numbers that are return codes. And the idea of this process is, okay, the voter, when selects something, is expecting that it's challenging the system and expects that the system will return the code related to the candidate. Since this is a paper ballot, this is a paper voting card, only the voter knows which are the return codes expected. So the way that it works, the protocol, the cryptographic processes are, initially the voter selects the voting options using her computer. And these voting options then are encrypted, digitally signed, and sent through internet to the voting system. If something happens here, then the voter intent inside the cryptographic or the encrypted vote will not be the same that has been selected by the voter. But what is receiving the voting system is supposed that is the voter intent of the voter. Once the voting system receives the encrypted vote, it implements a first operation over the encrypted vote. And the result of this operation is sent to another component of the system that reproduces a similar operation of the encrypted vote. We are making operations on encrypted data. So the system, the voting system, and the other validation system do not know, any of them know which are the contents of the encrypted vote. So, but they perform the operations. And the result of the operation is sent to the voter. Okay? Since the vote, if the vote contains the selected voting option of the voter, the return code here should be the same one present in the voting card. If something happens, for instance, if the voter has any malicious software, any malware here in the systems, bug, whatever, if somebody tried to change the voter intent, what would happen is that the code returned will not correspond to the selected voting option. So the voter then can decide, okay, I think that the voter intent in the ballot box is not the same one that I selected. So I prefer to they can invalidate the vote, or they can use another channel for voting. So using this process, at least we can provide some transparency to the voter. Since the voter can be sure that at the end, what is stored here is an encrypted vote that really contains the voter intent selected by the voter. In the other hand, if we go to the counting process, then we can check. One of the problems that we have is, okay, we have, at the end, we have encrypted votes that have been validated by the different voters. But how can we ensure that the decryption process is really providing the contents of these votes, and it's not, for instance, changing the votes and providing a different results just to manipulate the election? So we also need to provide some proofs that the decryption process is behaving properly. So usually in the counting process, and this is also used in Norway, the first step that is done is, what is not usually a mixing process, but is similar to traditional election of shuffling the ballot box before opening the votes to break the original order that the votes were cast. Since we have information about the identity of the votes, of the voters, sorry. So if we make a straightforward decryption of the votes, then it's easy to correlate the decrypted vote with the identity of the voter. So the first step is shuffling and re-encrypting the vote. Why re-encryption? Why we are making re-encryption? Since a re-encryption is another layer of encryption over the original one, and then change the encryption value, the ciphertext of the vote. So it's not possible, even if votes are in a different order after making this process, it's not possible just based on the value of the encrypted text to check that, okay, if they have the same value since we re-encrypted again. So the values will be different, but the contents are still the same. So here, what we made is we break any correlation between the original votes and the votes that are going to be decrypted. But what could happen here? This process can cheat. For instance, the election officials. And instead of providing a re-encrypted vote, they can change and put another vote. So we need to prove that this process is behaving properly. In this case, we are using in the case of the zero-knowledge proof of content. Why? Since we need to demonstrate that even these are two different ciphertexts and are in a different order, they still have the same contents. So none of the votes has been changed by another vote and another different vote. And this can be done using these advanced cryptographic techniques. In the other hand, once we have this, we can decrypt the votes and provide which are the contents. Again, here, we have another point in which the election can be manipulated. Since we have this encrypted information, we have this decrypted information, the only entity that knows the private key for decrypting this information are the electoral board. If they want, they can say, okay, I manipulate the election. I change the results. I provide this information, but nobody can see if these are the contents of this encrypted information. Again, using advanced cryptographic techniques, you can generate proof of correct decryption. So proofs can be generated here, and at the end, auditors and observers can use this proof for check that even these are different ciphertexts, they still have the same voting options, and when they are decrypted, the decryption process preserved the contents that were originally encrypted. So this process has been executed, but nobody changed the real contents, the real intent from the voter. Having this, then, we can generate the counting process. So if we add both processes, if we add the verifiability provided to the voter that can check that at the end, the votes cast really contain the voter intent of the voter, and that observers can check that the decryption process did not change the contents of the vote, then at the end is when we can provide the transparency. So the idea is, okay, we cannot provide transparency using physical means, but using these mathematics that are present in advanced cryptographic processes, at the end, if we have the data and we have these proofs, we can then detect if an election is manipulated or not, and then we can preserve the integrity of elections.